Okay, so I've planned two things for today. The first one will be an example, and I'd like to sort of emphasize this simply because it's good to have lots of examples in mind. And yesterday, I think we discussed two such examples. This will be the third one. Okay. That's the first part of the lecture. And in the second part, I would like to go back to the definition of a quadrature domain and reinterpret the definition so as to be able to put it in the framework of analytic geometry, so that we can use tools from several complex variables to understand this situation here. Okay, so so that's the plan. So let's start with the first topic. So example. So recall the theorem from last time, namely, if you have a bounded simply connected quadrature domain, then its Riemann map is a rational function, and this is an if and only if statement. And in fact, you can strengthen this theorem to say that you take all the poles of the Riemann function, the Riemann map, which lie outside your domain, you reflect them in the unit circle, and you push it forward by the map, and that's exactly the collection of nodes associated to the quadrature identity here. So, so let's keep this in mind when we do the following example here. So let's look at this classical map. So this is half z plus 1 by z. Psi is a conformal map from the complement of the unit disk onto C minus the closed interval minus 1, 1, conformal map. And the way this map acts is that if you look at a circle of radius r, say, then the map psi actually maps it onto an ellipse. Here is the interval from minus 1 to 1. Choose r bigger than 1. This is the interval minus 1 to 1. And the image of this is the ellipse. So let's call this E sub r. Okay. And as your circle sort of expands, this also fills up the whole thing here. So how do you describe the ellipse? ER. And ER is given by the set of points x, which is half of r plus 1 by r cosine theta, and y is half r minus 1 by r sine theta. So now we would like to use this map psi to create a Riemann map from the unit disk. So first of all, I'm going to scale this picture, shift r to 1. So rescale, and you get the map r psi of rz. This maps C minus the closed interval, the closed unit disk onto C minus closure of this ER bar. So I'm now radius 1. Conformally. This is the map psi of RZ. Okay. So what we can do is, I will first reflect this map to get a map inside the unit disk here. But reflection is conjugate holomorphic. So I need to take one more reflection. So what this amounts to doing is, looking at the map, z going to 1 divided by psi of r by z bar bar. Yeah. So r by z bar is going to take a point outside and bring it inside the disk. You start with a point here. R by z bar will take you outside, on which the map psi is well defined. But then I need to take one more bar here to get a conformal map. Okay. So this is a conformal map from unit disk onto its image. But then let's identify what the image should potentially be. The image should be, you start with the ellipse here, which is exactly the image of this circle. 1 over z bar is going to be the inversion of this ellipse under the origin. So I take this curve, the ellipse, subject it to the map 1 over z bar. I'm going to get a certain curve, and the interior of that is going to be the image of this map here. So this is going to be a domain which is the interior of the reflection of the ellipse ER under the map z going to 1 over z bar. To identify the image, we have to invert the ellipse. So let's do that. Right. Okay, so what is this map? Let's call this map phi. So phi is, I know what psi is, so just plug this in here and I get z divided by r squared plus z squared. And to do the computation properly, let's write this as u plus iv. These are the components of the map phi. So this is 2 divided by so this is r by z plus z by r. And I want to know, I want to eliminate the z variables, get an equation in u and v here. Right. So z here is of modulus 1. So this is 2 divided by, so write z as e to the I theta, because taking the image of the unit circle here. So this is r e to the minus I theta plus 1 by r e to the I theta. And if we do this properly, then what do we get? We get that 1 over u plus iv is half r plus 1 by r cosine theta minus half r minus 1 by r sine theta. I hope I got the signs correct. And this, of course, is u over u squared plus v squared minus iv u squared plus v squared. So to eliminate theta, just square and add. So eliminate theta to get u squared plus v squared squared minus u squared by 1/2 r plus 1 by r squared minus v squared divided by half r minus 1 by r squared equal to 0. So this is the inversion of the ellipse. It's a degree 4 polynomial, degree 4 curve. So this domain looks like this. It's sort of like two disks that are joined. Non-smooth only at these 2 points where there are 2 cusps. That's all. And you can actually write down what the quadrature identity will be. The identity will be, so there will be 2 nodes. And that's because of the nature of this map. So z squared plus 1 by z. Okay. So there are two nodes, and one can write this down, which is not able to complete. So let me not mislead anybody. There are 2 nodes, and just from a historical perspective, this is in the literature also called Neumann's oval, degree 4 curve to singularity. This is also a quadrature domain. Inverting an ellipse around the origin gives you a quadrature domain. Ellipse is not a quadrature domain by itself. It will always have a cusp.
So it
Cannot be smooth. Globally. Right. Yes, I think that's a true theorem. Yes. So Adimurti's observed that even in the examples from last time, there were always singularities. So there will be no singularities if and only if your domain is the disk, is a circle.
Okay.
I think that's true. Okay, we'll see. But anyway, the moral here is from examples 1 and 2 from last time and this one here, there's no dearth of quadrature domains there. And you can have as many nice quadrature identities as you want. Cusps are always finite. So we'll discuss a little more in detail today about that. What can we say about the polynomial, nature of singularities, and so on. Right. Okay. Now let's move on to sort of change tracks here a little bit and rethink the definition of a quadrature domain. So the very basic theorem that we proved last time due to Aronov and Shapiro says that if you have a quadrature domain, that's equivalent to 2 other things. First of all, your Cauchy transform has to be rational outside the domain. And more importantly, there is a meromorphic function, namely the Schwarz function. There's finitely many poles. It extends continuously to the boundary, and on the boundary it equals z bar. That's the idea, right? So for all practical purposes, being quadrature means there is a meromorphic function which equals z bar on the boundary. That's like a very nice working definition. So the viewpoint that I'd like to sort of share with everybody here is the following. Let's not.
You don't have a smooth domain, boundary smooth, which is quadrature, extremely connected.
except the circle.
Except the
Except the circle. Right. So I'm not sure, Kaushik, because in the equation I'm always going to have an R, and I really don't know. Maybe there's a critical value of R after which, but my first reaction is no. I could be wrong. Yeah, it'd be nice to check. I really don't know. All the images that you see of this Neumann's oval, I mean, they show you concentric pairs of these things, sort of expanding and shrinking. But an image is an image after all. After a while, it appears to be smooth, but I don't really know. Yeah. Yes, I'll talk about that. I'll talk about that. Yes. So one can estimate, upper and lower bound and something. So I think
depending on
number of poles. The number of poles will play a very important role. Exactly. Right. So to think about all this, I think it's good to sort of change our perspective. Let's not work in the plane anymore, but instead try to lift your quadrature domain to a bigger ambient space. So there is a way to do this, and I will illustrate this by giving you an alternative proof of a proposition from last time. Namely, that if you have a bounded domain, if you have a pair of meromorphic functions that extend continuously and take real values, then they are algebraically related. Yeah? Let's try to give a different proof of that. So take omega bounded and Fg meromorphic and such that F and G both take real values on R. So let's look at, so the easiest thing to do is to look at the pair of functions F comma G. So this is going to be a mapping from your domain into P1 cross P1 because both F and G have poles, right? And what does this map do on the boundary? Both the components are real. So on the boundary, this map takes you into R cross R. But I'll now compactify everything. Instead of working with R, let's work with the circle. So just apply a Mobius transformation to each component of the function F comma G. So let's look at the map F of Z minus I divided by F of Z plus I, GZ minus I, GZ plus I. Okay. So where is this a map from? So let's call this map capital Phi, and Phi is a map from your domain omega into P1 cross P1 and what does this Mobius transformation do? It takes each real line and maps it into a circle. So this takes values in P1 cross P1 minus a torus. CP1.
The torus.
Right. P1, right. This is the standard torus, S1 cross S1. This is a copy of R under this Mobius map. So the picture is this. So you have your ambient space. This is P1. That's another direction of P1. And you have your torus. And on this torus, you have an analytic variety whose boundary is in this torus. Okay. Why is the boundary of this variety? So first of all, this is a variety because phi is a proper mapping from omega into this space. It is proper because if you move towards the boundary, each of these take unimodular values here. Going to the boundary here means you have to land up inside T2. This is a proper map. And therefore, by the Riemann-Stein theorem, its image is in fact an analytic variety in the target space whose boundary is contained in the torus. Analytic variety. Pure dimension 1. Oh, sorry. OD. Right. And now, well, on P1 cross P1, we have the notion of a reflection in the torus T2, component-wise. Z1 goes to 1 over Z1 bar, Z2 goes to 1 over Z2 bar, component-wise reflection. So look at sigma. And this actually defines what is called a real structure on P1 cross P1, right? So reflection on P1 cross P1. Okay, so what we'll do is, let's give this variety a name. So I'm going to call this as A, say, A for analytic. So A is a variety with boundary in the torus. Using this reflection, I'm going to reflect capital A star. So how do you reflect, how do you get A star? Well, so A star. So locally, if A is defined by equations of the kind Fj equal to 0, say, yeah, then A star is going to be in the reflection of this. This is going to be defined by equations of the form Fj 1 over Z1 bar, 1 over Z2 bar equal to 0. So that's the local description of this analytic set. Okay, so A star is also an analytic set, analytic variety of pure dimension 1. It's just a reflection, a mirror image. And these two have their boundaries T2. So there is a very nice classical theorem of Alexander and Becker, dating from the early 70s. This was a time when there was a lot of interest in understanding this very classical problem. You take a domain, and inside that you take a closed set, say E. In the complement of E, you take your favorite analytic object. It could be a variety, holomorphic function, current, whatever it is. Under what hypothesis on your analytic data and E does the variety or function extend? So removable singularities, that's what this is. So this is exactly in that same setting here. I have A union A star, which is an analytic set in P1 cross P1 minus T2. So your obstruction is T2 now. In the complement of that, you have A union A star. It has the additional property that this is symmetric under the natural structure on P1 cross P1, real structure on P1 cross P1. Right? So Alexander and Becker's theorem tells you that if you take the closure of A union A star, adjoin the boundary, a priori you can get a very complicated set just by adjoining the topological boundary. But their theorem says that A union A star closure is also an analytic variety of pure dimension 1 in P1 cross P1. That's the theorem. i.e., T2 is a removable singularity. So nothing bad can happen here. All okay. And and I think it's important to understand what this theorem is actually saying and why does it work in the first place? Why do you expect this? So first of all, T2, this is a real two-dimensional manifold. And in fact, you can check that as a subset of P1 cross P1 in this ambient space, this is a totally real set, totally real manifold. There are no complex tangencies. On the other hand, your variety has a complex tangent everywhere at all of its regular points. So you have a bunch of very nice complex tangents that are getting very close to your obstruction T2. What do you expect? You expect the limit of the complex tangents to also be a complex tangent. Where can this complex tangent, limiting complex tangent lie? It has to lie in the obstruction. But T2 doesn't have any complex lines there. So the moral of this theorem is that whatever analytic object you take outside T2, it cannot have uncontrolled oscillations near a totally real set. It cannot be badly behaved. And the proof of this theorem will actually tell you that your variety A is actually transverse to T2. If A is transverse to T2, A star is also transverse to T2. So they just meet up. That's the proof. That's the proof. Okay? So that's the moral of the thing. So A union A star closure is an analytic set. Yeah, so it is possible to describe what the singularities are, Gautam. So I'll say a little bit about that. So you're right, Gautam. You know, there will be two possibilities. One possibility, you will have one half of A with the half tangent joining up with its reflection with the reflected complex line. So when you take the union of these two half complex lines, you actually get an honest complex line in the tangent cone at that point. This is one possibility. Or you can have two things that sort of come together like this and give you only one half of a complex line there. This is what happens. The other things are sort of regular points. These are the only singularity. You can't have this. That's the thing. Can't have that. Yeah. Okay, so let's take this discussion forward. So now I have A union A star closure is sitting inside P1 cross P1. But then the nice thing about P1 cross P1 is that you know, this actually embeds in P3 by the Segre embedding. So let's describe what this is. So let's suppose that the coordinates in these two factors are x and y, and the coordinates here are z0, z1, z2, z3. Okay, so what is this Segre embedding? What does it do? So S takes this pair of points and it gives you the following homogeneous components. So x0, y0, x0, y1, x1, y0, x1, y1. Okay, so pairwise all possible products. So what is the image of P1 cross P1 and P3? Well, that's a smooth quadric. So P1 cross P1, S of this is described by the following quadratic polynomial. So this is P3 now. And here you have this quadric. I just draw this. This is P1 cross P1, S of this other. And this is a one-dimensional variety here. A union A star.
Boundary of the original domain omega is smooth, this coincides with the double.
This coincides with the double, exactly. It is exactly the formation of the Schottky double. Yes, it can be identified with that a very canonical manner.
And if the boundary is non-smooth, then?
The merit, Debraj, is here we made no assumption about the regularity of the boundaries.
So it is the Schottky double, whatever happens.
Whatever happens.
So you perhaps apply some kind of conformal map to smoothen the boundary out, and then is that what is happening?
That will ultimately be the picture, but right now there are no hypotheses on the boundary. No hypothesis, right? So the picture will become clear. That's what will emerge finally. Okay. Sorry, this is S of this. Okay, so when I push this thing forward, I get a one-dimensional variety in P3. So there has to be a polynomial that describes this. So let Q describe S, A union A star. Describe meaning it's in the ideal of functions that vanish on this. So I'll write Q as the sum of P alpha beta gamma delta. So I have Z0 to the alpha, Z1 to the beta, Z2 to the gamma, Z3 to the delta here. And the sum of these is fixed. Homogeneous polynomial of degree k. Okay. So if I write down what Zi's are, because of the Segre embedding, Q will then look like the following. So this is the sum of this coefficient. Then I have x0 alpha plus beta, x1 gamma plus delta, y0 alpha plus gamma, y1 beta plus delta. So this form tells you that any Q that vanishes on this one-dimensional variety is of this form, and this is in fact bihomogeneous separately in the x variable and the y variable, because the sum of the powers is fixed. This is the bihomogeneous polynomial. Okay. So therefore I can pull these things back. I take this Q, pull it back, come back to my local picture here. So there is a polynomial which vanishes on A union A star bar. So what is that polynomial going to be? So it's going to be, say, P, x0, x1, y0, y1. But now I want an affine description. So I forget the homogeneous coordinates and I work with P of x comma y, where x is x0 by x1, y is y0 by y1. Okay. So this defines A, in fact, A union A star closure. But what was A, by the way? A was the image of this proper map phi. The components are F and G. So capital X is F, capital G is Y. This is your algebraic relation between F and G. Okay, so this is the theorem from last time, and now let us try to analyze quadrature domains using this idea. Let's not work with the domain, let's lift. Absolutely, Andreotti. In this case, we can do away with that assumption. Yeah, never use that. Exactly. So with this viewpoint, the omega can be unbounded, and in fact, F and G could possibly have poles on the boundary now, because they'll ultimately get mapped to T2. Yeah, again the theorem will apply. So this, yeah, absolutely true. That's very nice. Real on the boundary, exactly. Real on the boundary. And in fact, this polynomial has another property which I should mention. See, P describes this variety, which is invariant under reflection now. Therefore, this polynomial P also has this property. And therefore, one can check this. P of xy is P of x bar y. This is why capital P has real coefficients. This was another part of the statement of the theorem from last time. So symmetry is inbuilt because of this reflection property here. So irreducibility, what we can do is, so we are in, so we have a pure one-dimensional variety in P1 cross P1 now. So codimension 1, so it's a principal variety. So there has to be an irreducible defining function. I can choose P to be irreducible. So now let's look at the following situation. Omega is a quadrature domain, which means that there is a meromorphic function such that S of Z is equal to Z bar on the boundary. Okay, so we are going to use some of these ideas here. So please keep this sort of line of argument in mind. Okay, the domain will disappear. We will have a domain sitting inside a variety with boundary in some abstraction. Okay. So now let's define this abstraction. So let's call this M. I think I called it M here. M. W equals Z bar. So this is a totally real two manifold. And the idea is, let's look at the graph of S. So S is a function on omega, it's a meromorphic function. Some poles are allowed, but it equals Z bar on the boundary here. So graph of S, this is Z comma S of Z. Z in. Now the graph of S is a one-dimensional variety in C2. But S has poles, so I have to be careful. It's a variety in omega cross P1. And where does the boundary lie? Boundary of graph of S. This lies in all the points of the form Z comma Z bar, because S is equal to Z bar on the boundary of omega. So they are sitting inside M, which is a totally real manifold. So we have the same setup here. Okay, so the theme now is to understand omega enough to understand the graph of S. Okay. Just to make the exposition a little sort of transparent here, this is a totally real two manifold. I'm going to do a C linear change of variables and make this a copy of R2 inside C2. Okay, so let's do that. Just write all these things down for completeness. So let's look at z over 2 plus w by 2, and I have minus I z by 2 plus I w by 2. Okay, so this is a C-linear map which takes M into R2, sitting inside C2. Here is M, here is the transformation T, and this is R2, and this is I times R2. Okay. Now, we have a notion of reflection in R2, viewed as a subset of C2. What's the reflection? The reflection is given by tau ZW. Simply put bars on both variables. Right? If I have tau, which is an involution in R2, I can pull it back by means of T to get the involution in M. So that's your reflection across M. So this turns out to be tau inverse composed with tau composed with T. And if you write things down, this turns out to be W bar, Z bar. So the variables are flipped. So that's your reflection in M. So okay. So now let's A, which is the graph of S, and this is described by the equation, say phi ZW, which is W minus S of Z. This is equal to 0. And I'm going to reflect this now, A star. Reflection has to be done under this involution now. Okay. So let's draw a picture. So here is A, the graph of S. And this is my reflection, A star. So A star is the reflection of A, and just like what we did here, you can describe the defining functions by means of the involution. So this is going to be given by phi of W bar Z bar equal to 0, and this turns out to be Z minus S of W bar. Please take a note of these two. The variables have been switched. Okay, so as before, let us look at A union A star. This is a pure one-dimensional variety whose boundary lies in M. And therefore, by the Alexander-Becker theorem, this is an analytic variety in P1 cross P1, i.e. M is removable. Okay, so following that line of argument, so let P be the defining equation for this, again in affine coordinates and so on. P of x comma y defines A union A star closure. And because this is invariant under this reflection, T inverse tau P, the polynomial P, must also be invariant under the same real structure. And therefore, it turns out that P of x comma y must be P of y bar x bar bar. Okay. What this means is that if you write P as the sum of C alpha beta, x to the alpha, y to the beta, then C alpha beta is C beta alpha bar. So that's the conclusion that we get. And now let's analyze this variety a little bit in detail to get more information about the quadrature domain. Okay. So here is A union A star closure, which is defined by P equal to 0, P having that extra property. This is a subset of P1 cross P1. So I can look at the projections onto the separate factors here. The natural projections. Okay. Both of these are compact, therefore these projections are proper. And none of them shrinks this variety to a point, because what is A after all? A is the graph of a holomorphic function, a meromorphic function. So A consists of points of the form z comma s of z, where z belongs to your domain. Right? So when I push this forward down below by pi 1, I cannot get a point. A star. A star is described by this collection here. It's a reflection. And if A does not shrink to a point by pi 1, neither can A star, because they are just reflections and you're taking two different projections which capture the first and the second variable respectively. So these are proper and surjective in fact. Anytime we have this, these are actually branched coverings of P1. And this is in fact a holomorphic correspondence of pure dimension 1. So correspondence, just a fancy name for a variety in a product domain with proper projections on the factors, that's all. So I can think of this as the graph of a multi-valued map. So I start with the point here, look at the fiber, it's going to have finitely many points, push it down by the second variable here. So a point gets blown up to finitely many points and vice versa. Okay. So now, if you have a branched covering, the cardinality of the fiber remains the same when you count it with multiplicity, it doesn't change. So what I could do is, let's look at all the points where S has a pole. So the nodes of your quadrature domain, for example. If Z happens to be any one of these nodes, then the second variable is infinity here, because S has a pole there. So if I were to look at the pre-image of infinity, the fiber consists of precisely all the nodes here. Nothing more gets captured, because S has poles only at the nodes. And therefore the cardinality of this fiber is reflected by the nodes along with the number of derivatives that are allowed at those points. So it's the nodes counted with multiplicity. That's the cardinality of this projection. So let's write this down. So observe. Pi 2, cardinality of pi 2 inverse is number of nodes with multiplicity. So let's call this as capital N. Right? So I can write down my polynomial P of ZW right here as W to the N P0Z plus W to the N minus 1 P1Z and so on. That's P capital A. So this is your defining function for A. And a similar argument tells you that if you work with, again, counting the number of nodes and so on, you can show that phi 1 also has the same number of elements in the fiber here. After all, whatever information you have about one side also holds for the other one. So, both have multiplicity n. So let me write down the polynomial in this form. And the degree of each pi is no bigger than n here. So let's plug in points of this form s comma s of z to get w, so s of z to the n, p0 z, and so on. This must be 0 on your domain omega because that's your algebraic relation between z and s of z. And I can rewrite this now in a slightly different form. P0z is minus P1 by S, and so on, S to the n. Okay, now take a look at this and evaluate the right hand side at the nodes of the polynomial of the quadrature domain. S has a pole, so this right hand side vanishes. And how many such points are there? There are exactly capital N of them. So P0 is a polynomial of degree exactly capital N. And therefore, the defining function P of ZW has a very special form. This is W to the N, Z to the N, times some constant. All constants are going to be real because of that property there, plus stuff here. And therefore, the boundary of the domain, your quadrature domain, is contained inside P of Z bar equal to 0, because Z bar is equal to S of Z on the boundary. And this looks like CNN, Z to the N, Z bar to the N. This is x squared plus y squared to the capital N plus lower order terms. So the polynomial P, which describes the boundary of a quadrature domain, must have the sum of squares as the leading term. And the degree here is exactly the number of nodes counted with multiplicity. And this also shows that an ellipse cannot be a quadrature domain. Cannot write it in this form.
What is the equation of normal? X squared plus y squared to the power 2 plus something.
We did that. Remember, u squared plus v squared squared minus u squared minus times those constants. A degree 4 polynomial. Right. This is what happens. So anyway, maybe tomorrow I'll discuss the structure of the tangent cone, what really happens at the singularities, and then indicate the density theorem, one variable here. I'll stop here.